we start? Okay, so this is actually the first EMG seminar. First speaker is Lars, who will be talking about semi-stable perturbation problems for canonical metrics.
Yeah, thank you very much for the invitation. It's great to be here. I already feel it's very productive, so I'm looking forward to the next weeks as well. Yeah, so the goal of this talk is sort of to advertise a technique more than talk about the specific result. And this has sort of come out of several projects, and a lot of it has been with Rui. So a lot of the ideas come from him, and it's sort of been, yeah, a process over several years to come to the point where we sort of feel this is a good strategy for solving these types of problems. So since it's the full program seminar and not the complex geometry seminar, I want to start a bit by talking sort of about the area in general. So this concerns the existence of canonical metrics either on manifolds or bundles over them, which in some way are related to algebro-geometric notions of stability, and there's sort of infinite dimensional moment map pictures for these equations and so on. So the prototypes are the Hermite-Einstein equation on vector bundles and the CCK equation on manifolds. So the equation that we have, we will have some equation and some notion of stability. And so for bundles, we have the Hermite-Einstein or Hermite-Einstein equation, which says that the contracted curvature is equal to a constant multiple of the identity on a vector bundle. So this is on a vector bundle E, holomorphic vector bundle. And so here I'm fixing some Hermitian metric on E, and I'm varying the D bar operator. You could also view it as fixing the D bar operator and varying the Hermitian metric. But maybe I'll take this point of view for this talk. And then on the stability side, you have then slope stability, which says that the slope, which is the degree divided by the rank, decreases in subbundles. So, or subsheaves really, but yeah. So we want this for all proper subsheaves of E. And so this is the algebro-geometric notion that guarantees you the existence of a solution to this PDE. And here this is known that this notion, or the polystable version of this notion, is equivalent to the solution to this PDE. So this is the Kobayashi correspondence proved by Ullenbeck, Yao, and also Donaldson. So yeah, correspondence. Kobayashi correspondence. On the manifold side, we have the a similar story where we have the CCK equation, which says that the scalar curvature of some K&auml metric is constant. And the algebro-geometric notion here is called K stability, which again is some numerical criterion it requires that the Donson-Futaki invariant is positive for all non-trivial test configurations. And here I should have said the relationship between L and omega here is that the class of omega is the first Chern class of L, and you have the same here. The class of this metric omega is the same as the first Chern class of this ample line bundle in this case. And here we also have a correspondence, but here it's a conjecture. Here we have the YTD conjecture that predicts that this or some variant of it should be what guarantees you the existence of a solution to this problem. So those are the sort of prototypical equations that I'm interested in. But what I say holds for much more general canonical metrics. So it includes things like the deformed Hermite-Einstein equation in the large volume regime, or the set critical equations that Rui and I came up with together with John McCarthy, or Rui's notion of set critical metrics on manifolds. But I'm focusing on the things that have to do sort of with the large volume limit, so it's a little bit different than the considerations for things like the J equation that Mansi has been talking about in his course. So it's sort of more in the large volume regime than the low volume regime, which is where that kind of behavior happens. So I'm going to start with an example problem that's going to sort of follow us through the talk and illustrate the method that I'm trying to advertise. So the example that I will focus on a lot is on perturbation of Hermite-Einstein connections when you're varying the polarization. And there's a lot more you can do, and I'll comment a bit on the things you can do in the manifold case as well, but this is sort of the example that I will focus on and sort of talk about what you do in various degrees of generality. So the first case that I want to talk about is the stable case. So E is now a slope stable vector bundle with respect to some polarization L, and so we can solve that the contraction of the curvature is equal to some constant C 0 times the identity on the vector bundle. And what I want to do now is I want to vary the class, so I want to vary really the form here, omega, and see if I can solve this equation for nearby forms. So what I want now is to show that for all epsilon sufficiently small, so here epsilon could be either positive or negative. In some problems it is a positive parameter, but here it can be either way. So I want to show that then I can find a sigma, which is a section of NE, and this is a constant, and these depend on epsilon, such that I can solve the same type of equation, but where I now have changed the form that I'm looking at. So the way I change the B bar operator is by acting by the exponential of this sigma, this endomorphism sigma, and then I want to solve this. And maybe the way I'll write it is that I want to solve that this minus the constant times the identity in E is equal to 0. So that I see that as a map, and I want to find the zeros. And The idea is to use the implicit function theorem or inverse function theorem to solve this. And so if you now look at the linearization of the equation, this is now the Laplacian in this case. So this is the map sigma c goes to the Laplacian with respect to omega plus epsilon alpha of sigma minus c times the identity. So this is completely in general, not using the stability assumption, but the stability assumption is used to have a solution to begin with, but it's also used to say that this is a surjective operator, the linearization. Yeah. So alpha is a 1-1 form on x. So a fixed 1-1 form now. So alpha is so I'm sort of closed. Thank you. So I'm varying my symplectic form x. But really, you should think of it as being not exact, so that you are actually changing the cohomology class. So one way that the stability assumption comes in now is that stable bundles are simple. So this implies that the kernel of this Laplacian is just the identity. So that means that this is a surjective operator. And moreover, we can invert this sort of with uniformity in epsilon. So we can have an inverse. We have an inverse for each epsilon, but we can do that so that the operator norm of that inverse is sort of bounded from below by a constant. So we can bound this. So we can bound the inverse uniformly for all sufficiently small epsilon. And then we get a solution to the problem. Since just as epsilon goes to 0, if we just plug in our original d bar operator that solved the equation when epsilon is 0, this goes to 0 as epsilon goes to 0. So sort of because we have this uniformity and we are getting closer to the solution with epsilon, that means that for all sufficiently small epsilon, we get a solution to this problem. So this is the stable case, and it, and there we can always perturb, and the proof is this. So now I want to move on to sort of, easing up what I'm assuming. So the next thing I want to discuss is the polystable case. So now E is still Hermite-Einstein-Mills, but not simple. So if we let K be the kernel of the Laplacian with respect to any Taylor class, really, this now it always contains the identity, but it's strictly bigger. And so when we're doing this step, that means that we can't sort of at the linearized level prescribe the scalar, the curvature modulo constants. We can prescribe it modulo things in K. So therefore we sort of, even though we have a solution when epsilon is equal to 0, when we move to other polarizations, we can make sure that we land in K, but not that we're actually a constant multiple of the identity. So we can only prescribe the curvature modulo is K. And actually, E in this vector bundle setting, if E is polystable, then E splits as a direct sum of stable bundles with the same slope. Yeah. So that means that on each of these pieces, we can produce a Hermitian-Yang-Mills connection. And then that is Hermitian-Yang-Mills precisely if all of the slopes of these remain equal when we go to the new polarization. So, so using the Hermitian-Yang-Mills connections on the individual EI, so with respect to omega plus epsilon alpha, we see that this has a Hermitian-Yang-Mills connection if and only if the slopes remain the same. So now H is the polarization of alpha. Okay. So we can solve a more general equation in exactly the same way as in the stable case, but we can't necessarily solve the Hermitian-Yang-Mills one. Okay. Any questions so far? Yeah.
You said can only prescribe what?
The curvature modulo K. So at the linearized level, I can say the curvature is going to be this up to things in K. So the kernel, the image of this operator, since it's self-adjoint, is the L2 orthogonal complement to the kernel. So that's why I can do things modulo the kernel. And yeah. So there's a very similar story in the manifold case that I will just maybe say in words. If you look at the same problem for CCK metrics, then if you assume that X has no automorphisms, then if you start with a CCK metric, you can perturb the class to produce new CCK metrics. That's a theorem of Lebrun and Simanka. But if you have automorphisms, then you can't necessarily produce CCK metrics, but you can produce extremal metrics. So this is sort of an analog of extremal metrics for vector bundles. And there are loads of other problems like this. I mean, I mentioned you can produce a connection whose contracted curvature lands in K.
Oh.
Yeah, so it's going to be basically a sum of the slopes times the identity on EI. I'm going to push it up in a second. Yeah. Yeah, maybe I shouldn't write as far down. Yeah. So yeah, there are many other such problems. For example, with blow-ups or vibrations that many have worked on, including Rui and I, and also Anna Maria. But I'm going to just focus on this style of problem now, and also all the other kind of canonical metric equations that I described in the beginning are sort of like this as well. But so the question that I want to spend the rest of the talk discussing is what if E is okay, strictly semistable? Yes.
Does it take for, let's say, every time a small epsilon, or is it actually true as long as it goes by default for epsilon?
No, it's like sufficiently small epsilon. So for each I, there is a sort of interval in the epsilon parameter where you can solve it, but you can't do it for the whole helical necessarily. And so it's in that interval where you have solutions for all of them using this that you have this statement. But certainly this is a necessary condition in order to have a Hermite-Einstein equation. But far away from omega, other subbundles of E come into play. So now I want to focus on when E is strictly semistable, and what I mean by that is that E is semistable but not polystable. So it's destabilized by something, but it's not that it splits like that. So under this assumption in this problem, then we have a non-trivial subsheaf really, but I'm going to assume it's a subbundle that destabilizes E. Since it's semi-stable, that means that the slope of S is the same as that of E. Ready? Yeah. Thanks. Yeah. And for simplicity, I'm going to start by assuming that S is the only such subbundle, so that E is sort of an extension by two slope stable bundles. Okay, so for now, let's assume S is the only such. So that E is an extension of S by some Q, and SQ are actually slope stable with respect to L. Then S plus Q, this is now the same smooth vector bundle as E, but with a holomorphic structure which is not biholomorphic to that of E. So now I'm assuming E is simple as well. Yes, I said that. Yeah, so I'm assuming that these are locally free. Yeah, which is not guaranteed. Yeah, but this is now polystable. So sort of our previous discussion applies to that. And if the sort of perturbed slopes of S and therefore Q are the same as that of E, we just have the story we just had with the polystable case. But now we want to see if we can get, when we perturb L, that we can sort of make E go into the stable part. So if we want E to be stable with respect to a perturbed polarization, we certainly need that the slope of S becomes smaller than that of E. That's a necessary thing from the algebro-geometric side. So we certainly need, so to get Hermite-Mills on E, we need that when we perturb the polarization, the slope of S becomes smaller than that of E. Now it's equal at epsilon equal to 0. 0, sorry. But we want it to become smaller. And the hope is then that this is the only obstruction. Okay, so we want to say that under this condition, we can solve the Hermitian-Mills equation on E. So we want to show that this is sufficient analytically. We want to show that this is sufficient. And we're going to use sort of analytic methods. And the same style of argument as we did in the previous cases, but now complicated because we know that it's not always the case that we're going to be able to solve it. We need this condition to come up somewhere. All right. So I'm going to spend a little bit more time with sort of, so as I said in the beginning, we have thought quite a bit about this sort of problems, and we have gone down some routes that are maybe not the optimal routes. I'm going to now go a bit into the non-optimal route to sort of see a bit in the same style as this, where the relationship between the stability thing and things come in, but then I'm going to go to the better strategy towards the end. It's very important that I make it on time, because otherwise you just see the bad method.
One also expects to find Gieseker, the polymorph summation.
Yeah,
it's the Gieseker equation, right? The Leon.
Yeah, that fits into this style and framing.
It fits into, but it's not. I mean, a slope semi-stable bundle can be Gieseker unstable.
Yes.
Yeah.
Yeah.
Yeah. So it can go either way, and you need a condition to be able to, which is Gieseker stability.
So just for slope semi-stable.
Yeah. So you can perturb the equation sort of to this almost thing where you want Gieseker stability to be the thing that guarantees you a solution. Here we're perturbing by perturbing the polarization, but having the same equation, the Hermitian-Mills. Okay. Okay. So I'll try to do this a bit fast. But so let's go back to the polar stable thing that we have. So on S plus Q, we have a Hermitian-Mills d bar 0 with respect to omega. So when epsilon is equal to 0, this is the thing that has a Hermitian-Mills connection. And if we wanted to solve the equation there rather than on E, we would have wanted to solve, the equation would have been this. And then the issue there sort of was that we can only prescribe thing on the linearized level modulo K. So the linearization here. So which is the Laplacian with respect to omega plus epsilon alpha and sort of the 0 complex structure. This is surjective no longer modulo constants, but surjective modulo this K that I wrote before, which in this case is the identity on the S component plus the identity on the Q component. So the image of this is the orthogonal complement of this. And as I said before, if these actually remain equal, then we have a Hermitian-Mills connection on this bundle and not on E. And now we're going to see what happens if we assume this. So yeah, now we want to see what happens for E. So for E, we now know that the debug operator there is going to be this dbar operator on S plus Q plus some gamma, which is a 0, 1 form with values in ND. So, because this is the same smooth bundle and they are different dbar operators, and always you can, every dbar operator is 1 plus a given 1 plus something, which is a 0, 1 form with values in ND. And the curvature is so I'll not add the epsilon now, but I mean it would have been the same whether or not you included the epsilon, but this is now the old curvature, and then plus 2 terms. This first one is not going to be so important, and then the second one is the one that's sort of important. Here, A is gamma minus gamma star. So that's how the curvature changes. And if now I put in a parameter here, t, then the curvature changes like t here and t squared there. And this is how you can see that we're sort of infinitesimally close to solving the Hermite-Einstein equation on E, because as t goes to 0, we're approaching this, which is Hermite-Einstein. But we will never be able to get to a Hermite-Einstein connection for this K form, but when we change the class, we might. And then if we go back to looking at the linearization, then we see that the linearization, when we add the epsilon parameter, now we see, okay, we have this is now going to be the one at 0 plus OT. And note that this is invertible modulo constant multiples of the identity, but this is only invertible modulo K. So the things that the leading order term in the expansion here can hit is smaller than what the full operator can hit. But the things we can hit depend on, like how big the things we are that we can hit are, depends on t. So sort of the operator norm of the inverse to this one will depend on t and get small as t gets small. So in fact, so the norm of the inverse is OT squared. And since this is OT squared, that means that no matter what sort of, I want to choose a relationship between t and epsilon in a good way. And no matter how I choose that relationship to be, I will not be able to affect the projection to k of this term, because this is order t squared, and the norm of the inverse here is order t squared. So I will only be able to change things that are sort of worse than this once I start to try to solve the equation there. So that means that there's some kind of part here that I will never be able to get rid of. But that is precisely the part that I want to pair with the failure of this to be Hermite-Einstein. So what I want is to choose t such that the projection to k of this thing is a constant multiple of the identity. And then I can sort of solve my problem using implicit function theorem and that sort of thing. And maybe I'll say this a bit quickly. I said before, the projection of this will be mu of S times the identity on S plus mu of Q times the identity of Q. So this, I should write it. If I do this for the zeroth d-bar operator, so the d-bar operator on S plus Q, then I get mu L plus epsilon H times S times id S plus mu L plus epsilon H Q times id Q. So here you see where the relationship with the slope comes in, because the projection of this gives me that. And so what I want to do is I want to show that I can choose T in such a way that when I project here, I can make the projection of this plus this a constant multiple of the identity on E. If I can do that, I have sort of solved the most important part of the problem. But note that I have a T squared here. So I need that multiple that I get out of that problem to be positive. So the upshot is that this boils down to choosing T squared equal to mu L plus epsilon H of Q minus mu L plus epsilon H of S. And so I need, this is a real parameter, so I need this to be positive. That is precisely what my algebro-geometric criterion is saying. This is the necessary algebro-geometric criterion, that this thing is positive. So here it is an E instead of Q, but it's equivalent. Mu of S is less than mu of E if and only if mu of S is less than mu of Q. So okay, so that seems to work. So what is the problem? The problem is that if you want to do this in general, so in general, we have the Jordan-Hulder filtration like this, and then we can see, so this is E, and then we can see that as being like the d-bar operator is d-bar 0 plus gamma, where d-bar 0 now is the d-bar operator on the graded object, which is the sum of all of these quotients. And we have the same story there, but the problem is that it becomes just much more messy. So the shape of this gamma is now much worse. The way we act on gamma is it's not just scaling, and so it becomes a bit of a horrible mess. So Carl Tipler and I had an approach to this, which we ultimately did, but we had to assume a bit more on the gamma in order to make it work. Yeah, I'm never touching singularities. Yeah.
Just to recap what we're doing now, we are in a
So
strictly semi-stable situation.
yes, so E is strictly semi-stable and simple. So it has no, the only automorphisms are generated by the identity of E. And we're trying to, yeah, when we change L, we're still trying to see if E becomes stable, if it sort of gets pushed into the stable locus or pushed into the unstable locus.
So here in the semi-stable case, you don't have a solution, but then what do you get at the end?
So at epsilon equal to 0, my initial polarization, I don't have a solution. But you're sort of as close as you'd like to a solution. So you're arbitrarily close to having a solution. That's this thing with the scaling here. Like this has the correct curvature. So this, as t becomes small, becomes very close to solving the equation you want. But you can't solve it for the initial polarization. But when you change this, the hope is to produce a solution in the changed class. But you can get pushed into the stable locus where you should be able to solve it, or out of it. And the thought is that these slope inequalities, like we had mu L plus epsilon h of S smaller than that of E, that's enough to guarantee the existence of the solution. So that's the thing that's supposed to guarantee.
Direction.
Yes.
Always stable.
It is stable, so it doesn't have automorphisms. So yeah, it's stable. But it can be pushed either way. Like it depends on where these inequalities go. Okay. So under some assumptions, like this kind of method can be made to work. But it's not the best way to go about it, we've found. So here's some an outline of a better method, which relies on it has sort of two ingredients, which is work of Rui with Michael Hallam and work of Rui, John McCarthy, and me. And here what we want to do is to first reduce to a finite dimensional problem through the work of Rui and Hallam. So I'll just call it DH. So they have a framework for producing moment maps in sort of a wide generality that lends itself very well to these sort of questions. And in particular, what you get out of that is that you can first start by solving an easier problem using the implicit function theorem, and then you have a finite dimensional problem that you want to solve. So this is a general framework for producing moment maps when you have sort of universal families. So you have some U over V, and here, maybe I'll just say it here, I have a Kähler metric and I have a moment map. I have some K action that's equivariant here, and it's a way to push forward what I had here to a moment map here on V. So for example, if you're in the manifold case, the sort of thing that you get out of that is that the projection of the scalar curvature to this K that has been floating around is 0. That's equivalent to a 0 of the moment map through this general framework. And should I? Yeah, I'll say just a little bit about that. So, so what I have is that we have a Kähler metric, relatively Kähler metric, on U, and we have a moment map for that. So now this is the manifold case, really, but they have similar statement for vector bundles and for other similar type of equations. So they have it for really a lot of different equations. But then you can produce a moment map on the base of this submersion, which is at a point V equal to the integral over the fiber at V of the pairing of the original moment map at that point paired with the scalar curvature of the fiber times the volume form of the fiber. So zero of this moment map means that the scalar curvature is orthogonal to these things on the fiber. In particular, if you can ensure that your family is such that the scalar curvature actually lands in K, then having a zero of this moment map means that you have solved the CCK problem on the fiber. Okay, so the starting point for being able to use this is to ensure that your family has scalar curvature which lies in sort of K. But that's an easier problem in these problems because it's sort of that just uses the leading order asymptotics of the linearization of your problem. And they had, so now I said what this says for when you do sort of the CCK problem, but you have similar statement for bundles or like for set critical things, and it's really a big generality. But yeah, the moment map is saying that some projection is zero, so you want to ensure that the things orthogonal to that projection is zero before you start it if you want to solve the CCK problem on the fibers. Here, that's the important part. And it's a moment map with respect to some sort of Weil-Petersen form on the base. And for this problem, that's positive. For the Hermite-Einstein thing, it's positive, but in general, that's something that you have to check that it's actually positive. It's some form that gets defined, which may or may not be positive. You can still talk about having a moment map for that. So if you actually want to apply it to solving these types of problems, you have to check that that form actually is positive. So that's one of the ingredients that goes into the sort of better method. Yeah. So this is a holomorphic submersion where the fibers are compact. V and U don't have to be compact. So you can think that V is some ball in a vector space or something. And yeah, but the fibers have to be compact. Yeah. And then the second ingredient that goes in is some flow technique. So this was used in the set critical paper with John Rui. So that was joint with Rui and McCarthy, and it's building on sort of local Kempfness type things. We used this book by Georgelas, Robin, and Salomon, and also work of Chenningston for this part. And this gives a local Kempfness. Which we then apply to this local setting here, V. And it produces a sort of a dichotomy. Either you have a zero of the moment map, so you get either a zero of the moment map, either a zero moment map, or you degenerate. So in the orbit that you're in, or you degenerate V to some other point in V, where you have some non-positive weight. And then the whole point is so the remaining point is to say that this weight that you get in this framework is actually the algebro-geometric thing that you were looking at to begin with. So this in the bundle setting, that comes from this projection. It's really sort of the projection to K that you get that weight is related to the slope. And yeah, so if you have all of these ingredients, you manage to show that you can make the curvature orthogonal to K in the family that you have, that the form you get here is positive, and you manage to relate that the weight that you get out here is actually related to the algebro-geometric weight or stability criterion that you anticipate. Then you can use this framework to produce a solution, because then, assuming the algebro-geometric thing, you get a zero of the moment map, and a zero of the moment map then means that you actually have a canonical metric undefined. All right, thank you very much.
Questions? So, begin with, why is the norm of the inverse there or
Yeah, so I mean, the operator is OT, I said. Yeah. But if you recall the expansion of the curvature, it's like the original curvature plus D0 of A plus this A wedge A. D0 of A is sort of off diagonal in the decomposition of S plus Q. And so that actually doesn't hit the part you want to hit. It avoids K altogether. And so it's the T squared term you need in order to hit K, some new part of K.
Sorry, at the end of the day, I mean, order by order, you're doing something. How do you put this together?
Yeah, so you do order by order, and then you apply the implicit inverse function theorem for the linearization of sort of with respect to del bar t, which is invertible, but it's invertible at a worse order than like constants. It's order epsilon squared or something like this. So you need to have a much better approximate solution in order to perturb. So there is a type of implicit function theorem which says that if the operator norm of the inverse is this size, then you can hit everything of this size nearby what you had. So when you work out what the sort of relationship between the rates are, you figure out how good about an approximate solution do I need in order to guarantee the existence of a solution to the problem.
And so this local chemistry, this is a bit confusing. That so I mean, why doesn't, I mean, if you keep acting the group, why don't you fly out of the?
Yeah, so that's very important. So a part of it is so you see it. The thing is, when epsilon is 0, the flow is sort of doing a good thing. It stays near your original thing. You might not flow to 0, but you flow sort of to nearby things to 0. Yeah. You can also flow to 0, but yeah. When you perturb, what you want to say is that so you know you're not going to be flowing to 0. So if you're sort of very close to 0, you're actually supposed to be flowing away from it. But you want to say that there's some region where I know I'm heading in the right direction. So if my approximate solution is too bad or something, then I know that I will flow in the right direction even when I've changed a little bit. That's very vague, but yeah.
Basically, these perturbation problems, the flow always remain in the neighborhood of the origin, in the relevant orbit. And that's the point. So it's really, when we use this book, it's to go from results that the flow to kind of stability results. And one of the main points is to show that the flow does actually stay inside.
Yeah, that's one of the main points. Maybe heuristically, like, okay, so let's say that this region is the orbit of the V. Then when epsilon is equal to 0, I know that I'm sort of heading this way. When I have perturbed epsilon, I might be heading out if I start here, but maybe on this boundary bit, I'm still heading this way. So I know I remain in this region. Even though the thing I'm supposed to hit is maybe moved here instead of here, I still remain in this region. So that was an important part in showing this that way, to show that you do remain, that you don't flow off somewhere. Not that I'm aware of.
No, I mean, that's somehow the key difference between these problems and the problems that have been talked before. I mean, in those problems, stability is topological because everything is semi-stable. So stability just means that the orbit is closed. Okay. So here we've got a non-closed orbit because 0 is in the closure of the orbit. Okay. So it's completely different, basically. I mean, you have to use the kind of advanced Kempf-Nest technique rather than the actual Kempf-Nest type techniques. And really what Sektnan uses is the actual just literal Kempf-Nest theorem of Kempf-Nest, which is when stability is a topological equilibrium.
So can you elaborate a little bit more on how you would use in general this pan-dimensional flow problem?
Yeah, so here, like, let's say I was doing the constant scalar curvature problem, just like this, and I start with my initial family. Then having is
So that in that case, you sort of can involve, let's say, the coordination theory.
I mean, even if you don't do something to begin with, you could still have applied this flow stuff, but then you would have solved the problem of the scalar curvature being orthogonal to K. That's the problem you would have been solving under the assumption that you have under the algebro-geometric assumption. But that's not the problem you want to solve. You want to solve the CCK thing. So that's why the first step is to perturb your given family to one where this actually lands in K. I don't know if that exactly answers your question, but that's sort of the order of it, because if you did it the other way around, which is actually what we sort of did in me and Rui and John, because that paper came before Rui and Michael's paper. So the order is a bit different in this than this strategy. This strategy hasn't yet been used, really. Yeah, then after solving the finite dimensional problem, you're still left with a problem to solve because you have just managed to make it land in K, orthogonally to K rather than actually being constant.
Any other questions? Okay, let's thank Lars again.
Keep.